This is the first of two videos covering this PowerPoint presentation, which looks at graphical techniques and linearization. Beginning with the purpose of linearization, really there's two purposes. One is to either validate or to determine a quantitative relationship between two variables. The second one is to determine to use the practical data to determine a physical constant. So for example, we can use an experiment and all the data that comes from that experiment to determine a value for gravity. I'm using the first video here looks at the benefit of using a range of data when exploring a relationship. And to do this, we're looking at an example using Newton's second law. So the setup here shows a possible practical method of exploring the relationships between force and acceleration. And the students that set this up then, I refer to in the first part of the video here, are proposing that we can apply Newton's second law, that is F net equals ma, to this system. And the students are proposing that we can vary the net force by varying the mass of the cradle over here, and that that net force should be able to accelerate the mass of the trolley, which is kept constant. So the data that comes from this has been determined and calculated here so that the trolley mass is actually 500 grams. The data we get from this experiment is pretty much correct, but we look at the benefits and the pitfalls of using single point versus a range of data. So to begin with, we look at single point data. So again, to reiterate this, then a student is proposing that W, the weight of this trolley here, of the cradle down here, is proportional to the acceleration. So that if we double the weight, we should double the acceleration. And further, the weight actually is equal to the trolley mass times the acceleration. So that trolley mass could be referred to as the constant of proportionality, which we could determine, therefore, by working out the weight here, the net force, divided by the acceleration. That would be determination of the mass. Assuming that this is correct here, the statement the students make. So that's what we're going to look at here. So that's essentially explaining what I've just talked about here. So this slide just looks a little bit at how we could practically measure the acceleration of the trolley. We could point a motion sensor behind it here, and we could record data. Motion sensors do transform the data to give us acceleration directly, but they're pretty poor at this. So typically what we would do is we would use the motion sensor back here, but we would record the velocity with time, and we would determine a line of best fit. And the slope of that velocity time graph would give us the acceleration. That would be one way. Another way would be perhaps to just simply release the trolley and let it move through a certain distance, and to time that distance. And we then have three variables: initial velocity, time, and displacement. So we could use an equation of motion to determine the acceleration. That's quite a common method that the AP students might use, for example. So anyway, we have some methods here to determine the acceleration, and we can easily determine the net force W. And let's do this. So Marcus then is a kind of hypothetical student in a group of three students who just uses one result and says, look, okay, we can prove this because we can certainly verify Newton's second law, because we can measure the acceleration, we can determine by calculation the net force, and we can see whether net force is equal to mass times acceleration using the data. So this data here would be realistic for a mass of 500 grams here, and for us a mass of 50 grams here. The weight would be mass times gravity, which is 0.05 kilograms times 9.8, which gives us our 0.49. So what Marcus could have done here is to work out the theoretical acceleration by taking the net force divided by the mass, which is the known mass of 0.5, to get 0.98, and compare it with the practical one of 0.9. Marcus could conclude that it's fairly close, given we've only taken one result, and therefore the practical result confirms the theory. We'll see later this is actually not true. The theory we've applied to this system is actually incorrect. This is the pitfall of taking a single point. What, by the way, Marcus could have done as well is Marcus could have said, look, we can use our results to determine the inertial mass if we didn't know it, because we could just use Newton's second law and say that the mass would be the net force divided by the acceleration, which is W divided by A, which gives us 0.49 divided by 0.9, which gives us 0.54 kilos, which is in close agreement to the actual mass used. So again, Marcus could be quite happy with his result there, and basically conclude that the experiment's gone well and that he was right with his predictions. But we have Jessie now, who's also in the group of 3 hypothetical students. Jessie decides, let's do another result, and so she adds to Marcus's result and doubles the mass of the cradle and determines the acceleration and gets this result. And then what she does is deduces here, like she's saying, we want to see whether the doubling the mass doubles the acceleration. She divides 1.7 by 0.9 to get 1.9, which she says is approximately 2 correctly, and therefore she says that we validated a relationship. Weight is indeed proportional to the acceleration. The net force is proportional to the acceleration. So again, she's pretty happy with it. She could also use her experimental results, like Marcus did, to find out the practical determination of the trolley mass, which is in this case the inertial mass, by dividing the net force by the acceleration to get 0.54 for the first point, which is what Marcus got, and for the second point, 0.98 divided by 1.7, which gives you 0.58, a little bit off, but within the realms of kind of experimental uncertainty. Then she's not too unhappy with that. But instead, we've got now Annette, who's the third hypothetical student, who says, let's do what the teacher said and collect a whole lot of data. So let's vary the mass here of the cradle right up from 50 grams to 500 grams. 500 grams is quite a large mass here, as heavy as the actual trolley mass. And we get the data here. Notice we've still got the Marcus's and Jessie's data, so we're carrying this on now with Annette, and she's done all the other results here, and she graphs them. And when we graph them, we realise that the first 2 points look like they were kind of headed for the origin and linear, but we really need more data to see that, in fact, it doesn't appear to be linear. So it could be we've got an increasing kind of uncertainty or external factor like air resistance, but given that this result could have been carried out with the trolley only just moving, air resistance wouldn't account for that curve. There seems to be something else incorrect, and this is what Annette is saying. There's a clear pattern, but it's not linear, it's curved. The range of data has shown that the theory does not seem to describe the relationship. If it did, it would be a straight line through the origin. You can't get a straight line passing through those points, even with error bars, to pass through the origin. So Layla then goes on, who's a bright spark in the classroom. He says, actually, this is because your assumption was wrong. The net force weight is actually not just acting on the trolley, it's also acting on itself. If you simply applied a force where the cradle was hanging, that would be different, but you're not just applying a force, you're hanging some mass there as well. So the weight of the mass has to not only accelerate the trolley, but it also has to accelerate the mass. So every time you increase the net force, you're actually increasing the mass being accelerated. So their assumption that they're keeping the mass constant was incorrect. A summary here then is that using a range of data to investigate 2 variables is preferable, since it allows us to observe the whole pattern and prevents us from making mistakes based on a limited amount of data. I'm going to do another quick follow up on using a range of data, and this is looking in particular at using a range of data to find a physical constant, the mass of the trolley. It will be, for the AP students, a valid method to find the inertial mass. So this time we're correctly setting up the system, so we're keeping the system mass constant. Because we're applying a net force here, we have to take into account the mass that we're also adding to the system. So we can increase the net force without increasing the mass of the system by simply moving moving slotted masses from the trolley to the cradle mass. So in this situation, we're going to have 500 grams for the trolley, another 100 grams worth of slotted masses, which you can move from here to here. And these students carry out the experiment and find correctly this time that the more that if you double the cradle weight, you do double the acceleration because you haven't varied the mass of the system. Now you could have taken any one of the points and determined the inertial mass using F net divided by A, but it's better to actually draw the line, use all the data to construct the line of best fit, and we get a line of best fit here. And if you compare what I've got here, which is what the Excel graph gives you, with what I've written here, I've just simply changed Y for acceleration. I've changed X for W because X is the cradle weight W, and I've just omitted the small intercept because that can be ignored. It's very close to the origin. So we've now got a practical equation, A equals 1.7 W. If we compare that, A equals 1.7 W with A equals F net over M, we can split apart the F net over M into 1 over M F net, and the 1 over M would be constant because we kept that mass constant this time, and it's of the form Y equals a constant times X, which, as we know, is a straight line through the origin, which is indeed what we got. But we can compare the constant we get from our data, which is the slope, with the theoretical constant 1 over M, and we can therefore use our slope to give us 1 over M, and therefore we can use the slope to give us the mass. The mass is 1 over slope, which is 0.595, which is 5 grams out of what we actually used using that data. If we used any one of those bits of data, it might have been quite a lot above or below the correct value for the trolley mass, but using all of them and averaging out the errors and uncertainties, we get our best possible, most valid result. So the summary here then is we should use a range of data to determine a physical constant rather than just one piece of data. It averages out the uncertainties. In an AP exam, you could get 0 for just using one result. You should always use a variation and use the slope method to find the physical constant. That, I believe, finishes the first part of this presentation. Thanks very much.